Okay, so thanks for the introduction. So we're going to talk about KSMBD and how we exploit it for kernel, remote code execution on the Linux kernel. So I'm Quentin, this is Guillaume. We worked on this with Arnaud and Flora. They're not here today, but they're part of this. We're security researchers, and we're part of Thallium. So it's an offensive security team, part of Thales Group, and we do reverse engineering and vulnerability research. So KSMBD was part of our spring break last year to, well, look into open source stuff. So what are we going to talk about in this talk? So first, we're just going to introduce KSMBD, what it is, how it works, then detail some of the vulnerabilities that we found, the ones that we are going to be using for the exploit afterwards, which we'll come to last. Okay. So what's KSMBD and how does it work? Right. It's an in-kernel SMB server. It's been merged in the Linux kernel with 5.15, so that was in October 2021. And basically, it supports RDMA and TCP transport. In this talk, we're only going to focus on TCP. Initially, it was for performance, but nowadays they say it's mostly to do things that are hard to do in userland. Okay. So SMB, basically, at the start of an SMB request, you have a NetBIOS, what's called the NetBIOS length. So it's the length of the actual request. So the server just has to read that length of the network and then accumulate data until it has the full request. That request is composed of a header and the command. That's a simple request, but you can have compound requests. Compound requests are useful. They basically chain several commands together, and well, in the SMB header, you just have an offset to the next command in the request, and the NetBIOS length at the start just covers the whole request, all the commands. Theoretically, you should be able to chain any SMB2 commands in a compound request. And it's used to reduce network overhead. For example, you can open a file and read it with one compound request. Right, so these are the types of requests. Now, if we look at a sample SMB session, what would happen first is that the client needs to negotiate the SMB dialect that's going to be used. At this stage, it's going to provide its GUID that will identify it to the server. Well, it's not authentication, it's just identification yet. Then there's the session setup. So this is where authentication occurs. This creates what's called an SMB session. So it's an authenticated context for any operations that might happen next. The client at this stage gets a session ID. Then the client will open a share that's called a tree connect. You get back a tree ID. Then you can open the file. That's an SMB2 create command. It can either create or open files. You get a file ID, and then you just read the file contents with the provided session ID, tree ID, and file ID. And then you can close the file, close the share, disconnect from the tree, and log off. Right, so that's a sample session. And so KSMBD, we're going to focus a bit on its architecture. So it's composed of a kernel module and user space daemon. So the kernel module is where most of the connection handling happens. So it receives it accepts new connections in a dedicated K thread. Then it will move them off in a connection handler that's another K thread. And this connection handler will spawn other K threads to handle separate requests. So most of the SMB commands are handled here in the kernel module. The file I/O happens here too. And there's also at some stage, the user space daemon will get involved for complex operation like authentication, share management, and some RPC endpoints that Dave was talking about earlier. Right, so it was done this way to keep things in a kernel for performance, but this means that you have complex code, because it's kernel code, and you have a complex protocol because SMB has a lot of commands that do a lot of things in the kernel, so it might not end up that well. And on top of that, you also have a root daemon because it's talking, the KSMBD daemon is talking to the KSMBD module over netlink IPC, so that requires at least capnet admin. So in this case, it's running as root. So those are both highly privileged components, and well, we thought it was worth to take a look at them. Right, so it's doing network and VFS stuff that looks, well, not trivial to fuzz, so we first went into it doing code review. So basically there are the main surface that you have as a remote attacker is the network surface of the SMB protocol. But the VFS surface is also important because as a local attacker, you could just play with files on the share and then access those files through the SMB protocol, and maybe you can again use useful effects to that mechanism. And lastly, the last component was the user space component doing RPC. All right, so first we're going to dive into PDU handling, basically the network surface, how KSMBD processes an SMB request. So that's the code from KSMBD. Basically what it does is that it just first reads the NetBIOS length of the network, that's 4 bytes. Then it will allocate a buffer of the corresponding length, read the rest of the bytes to form a full request. This will actually wait until all the bytes have been received. It will only block that connection from receiving new requests. It won't block other requests on other connections or other connections. It's a separate K thread. Right. And then, well, you just process the full request that you received through a work queue. And you do that with, KSMBD does that with a context that's KSMBD work structure that holds a pointer to the request buffer and various kinds of stuff you need for the request processing. Okay, so once we have the request and we schedule it on the worker, it's going to get bounce checked for each command in the request, and there may be several if it's a compound command, but each of them is going to get bounce checked, and then the command handler specific to that command, to each command, will get called. So for a request with a single command, well, basically you have a buffer, a pointer in the work structure that's request buff that points to the start of the command that you're going to be processing. Right, so this is the buffer that holds the full request. So this only works for single command requests. But if you have a compound request, you can't use that buffer because it only points to the first command. So KSMBD uses helpers, work buffers, to basically just get a pointer to the current command that's being processed in the request. So that means that when you process a command in a compound request, you should always be using this rec pointer that comes from the work buffers macro. That's the one that's pointing to your command. And if you see any use of request buff in the KSMBD code, usually it's not a good sign, right? It turns out there are quite a few of them. Well, most mean that the command doesn't work, it can't be processed if it's not the first one in a request. Well, it's a bug, but it's not that bad in itself. And the second thing that you have to note is that when KSMBD tries to access the NetBIOS length, it should only do so not through the rec pointer, because that one points to the current command, but through the request buff pointer, because that's where the NetBIOS length lives. Right, so what are the mistakes that we should look out for in KSMBD code? Well, if you start grepping for request buff, if you see that it's going get RFC 1002 length with that pointer, that's fine. It's just fetching the NetBIOS length. If you see that it's trying to access command fields through that pointer, this is not so good. And conversely, when you grep for rec, it's always named rec in KSMBD. That's very convenient. And if you see that pointer to the current command being used through get RFC 1002 length to parse the NetBIOS length, this shouldn't work. So this is usually very bad, a very bad sign in the code. But if you just access command fields to that pointer, it's fine. So with that in mind, we're going to move to some analysis of SMB2 write handling. So this snippet of code it just performs some check. You see in the check that there is the get RFC 1002 len call with the rec pointer, so that points to the current command. Then it computes the address of a buffer. That's the buffer to be written to a file, and then it performs the write to the file. So the check, essentially what it does is that it checks that the offset to that buffer plus the length of the buffer fits within the length of the whole request. Well, that's what it attempts to do. And it works for a single SMB2 write command in a request. But as soon as you have a compound request, that get RC1002 len with the rect pointer, it will parse whatever was in the previous command as the netBIOS length. So this is attacker controlled. So obviously, we can bypass the length check this way, right? But I mentioned earlier there was a bounce check in the start before the command handler is called. And that bounce check is here in the code. Basically, it checks that the offset plus the length fits within the bounds of the command, and it does handle compound requests correctly. So that means also that the check we saw in the SMB2 write handler is redundant, but this one should be enough. But for SMB2 write, there's an edge case, namely that if data offset, that's the offset to the buffer to be written, is 0, it will not use the data offset and the length of the buffer, it will use two other fields. Those fields are used for RDMA transports. That's the offset and length of the channel information for RDMA. But those fields are not used when doing the actual handling of the write command in the SMB2 write handler. So if we set data offset to 0 and those fields to 0, we will pass the initial bounce check and we'll just get back to the check we saw earlier, which will parse the length from the arbitrary padding that lays between two commands. And we will be able to write out of the data from out of the bounds of the request into the file. That's a leak. So after we do that, we just have to read the file back. And the next question would be, what do we actually leak at this stage? So to understand that, we need to do a bit of an intermission. We're going to take a look at the slab allocator. So it's an allocator that's widely used in the kernel. Its purpose is to allocate small fixed size objects. So basically what the terms are, you have a cache of objects. Each cache is made of slabs. A slab is a few pages of contiguous memory, and each slab is divided into fixed sized objects. So for example, here in kmalloc 256, you have each object that's 256 bytes, right? And they're all fixed size. And kernel code can create caches as it needs. Some of them will get merged. If there are similar characteristics, this happens. We'll get to that later. Right, so that's allocation. And there's another important feature of the slab allocator is that it has per CPU, per cache, free lists. And those free lists, they are last in, first out. So when you free an item in the slab, the next item that you will allocate will be that precise item. It's an important feature of this allocator. And the free list is initially randomized. That's a mitigation that prevents attackers from anyone trying to exploit the cache, the slab, from knowing the actual layout, predicting the layout of the objects in the slab. Right, so that was suballocation, and it turns out that our request buffer is usually allocated in a kmalloc slab. So we are going to leak from a kmalloc slab. And the nice property that we have is that there is no restriction on the padding that's between the two commands that we send, the first command and the SMB2 write command from which we start leaking. So we can add an arbitrary padding between the commands, and that allows us to choose the request length and then choose the slab from which the request will be allocated. That allows us to choose from which slab we will perform the leak. This is useful because different objects are located in different slabs, so we want to target a specific one. You can target a specific one that way. Right, so at this stage, we should also be wary of not leaking too far, because we basically have no upper limit. Well, the only upper limit is the maximum write length of an SMB2 request. It's quite huge, so we don't want to be leaking too far because we might run out of the slab and need to unmap memory. We don't want that to happen, so usually we try to limit our leaks to just the next slot in the slab. So this is our info leak primitive. We nickname it write leak, and now I'm going to give the stage to Guillaume for the write heap primitive.
Okay. And thank you, Quentin. So Quentin talked about the write primitive, which is kind of SMB message, and we're going to talk about the query info, which is another kind of message. This one is interesting because it lies on the border of adaptation that have been made to support Windows. Typically, this message is used to bring in the reply information about the file, such like, for example, in this case, a security descriptor, which is typically Windows stuff. In this case, KSMBD implements the query info with the specific info type requiring to get the security descriptor. And internally, it is implemented using extended attributes of the VFS and setting something called security.ntacl. So basically, when you make a query info, you got the information that is located in this attribute back in the reply. This is the function that is used to copy the value of the attribute set on the file in the VFS. And as you can see, there is a memcopy, and there is an input and output that is given, but there is no check of sizes, which means that in this case, we are likely to be able to control NTACE and NTACE size member, which means that basically you control the memcopy source pointer, the content of the memcopy, and you also control the size of the memcopy. Now the question is, you copy onto the SMB reply, and where is this reply allocated? This reply is allocated using this function, and especially when you make the different tests go away, you see that the reply is always allocated using 4048 bytes, which means that it will be allocated in the Camalog 512 slab. So we have a fixed size buffer, and we have a memcopy on which we control the pointer, the pointed value, and the size, which means that we can overflow. But the question is now, are we able to set or to control the security.ntacl attribute? The question is now, can we control the value of this? And the answer is yes, because there is also a setinfo command which allows to set this security file, this security descriptor on a file. And then later, when you call the query info command, you will just do the heap overflow, and you will overflow onto the reply, which is in kmalloc 512. So this is our second primitive, which is a linear heap out of bound write, and we have nicknamed it write heap. We have also talked about the DCE RPC surface, which is nice because the KSMBD mount D runs as root on the target, and everything that target the RPC, DCE RPC, will be tunneled from KSMBD to the user space, which means that if you find bugs in this is cool because you are reaching bugs in a UID 0 process in the user space. So we have vulnerabilities on this surface. We raise them to ZDI, and most are fixed upstream, but we didn't go that way to exploit, and we keep the kernel exploit for today. But keep an eye on our blog because we'll be blogging this later. This is the list of what we have sent to ZDI, and you maybe have heard about the CVSS 10.0, which is a pre-auth UAF, but we didn't use it for the exploit, so there is no way in getting into it. And this is a timeline, and sorry for last Christmas because it was a bit of a mess. Like, this is the public release of advisory, and it makes a lot of people work during Christmas. Sorry for that. Quentin?
Okay, so now we're going to be moving on to exploitation. So our context is that we have access to a KSMBD server. We have a share on that server. We can access it through TCP, and well, we want to breach that server. So it's going to be running a kernel with carrier CLR, so we don't know where the kernel base is. It has Howden free list. That means that that's the free list randomization I was talking about earlier about the slabs. So we can't predict the slab state. There are other mitigations that are not important to us, such as Howden user copy, because we're not a user process. We're just sending, we're a remote client, so that's off the table for us. Control flow integrity is off the table also because it's not shipped in the kernel we exploited, the Ubuntu kernel we exploited. Structure randomization also is not enabled specifically in KSMBD, and it was enabled more generally in the kernel later on, but on our target kernel 5.15, it's not enabled. Right, so the most local exploits can make syscalls, and they do have some well, various ways to have effects on the system to populate caches and everything. we basically can't do anything arbitrary like this. We didn't want to assume that we could and that we had access to anything on the system other than KSMBD. So we are only going to be working with SMB commands and try to exploit the kernel that way. Right. So in terms of configuration, we need a share. We need access to that share. So we need credentials. The share needs to be writable. That's for the leak primitive because we need to write the leak data will be written to the file and we will read it back. And we need to have the option enabled to enable extended attributes stored ACLs. That's used for the write primitive. So with that in mind, let's move on to the exploitation strategy. So we have access to the share, and we want to end up with a stack pivot into our own ROP chain and, well, further shellcode or whatever, right? So the first step for us would be to leak the kernel base because we will need gadgets at some point, and there is randomization, so we'll need to leak the kernel base, right? To do that, we'll use write leak, so we will leak information from the slabs. We need to know what to look for, ideally pointers in the slabs that will allow us to de-randomize, to compute the kernel base. So we set up a victim machine. It's running our target kernel, Ubuntu 22.04 with the kernel 5.15. And we ran a Dragon script to inspect live on the machine the activity in the slabs, in some of the slabs that we could target, and try to look for addresses in there and pointers. Right, so, and, well, we gather statistics on those, and then we trigger write leak repeatedly on a target machine, see what we leak, and we try to match the LSBs of the addresses we find in those leaks to what we saw when we profiled our target system, victim system. So, and that allows us to know what when we find matches, we know that this is an address of an object. We know the offset of that object to the base of the kernel, so we can compute the base at which the kernel has been loaded. So that allows us to defeat KSLR. This is using write leak. Now, next, we're going to talk about leaking KSMBD objects. So basically, we're going to use write leak again, and we want to know the address of data that we control, right? So we can craft our ROP chain in the kernel memory, and we want to reference it, right? So we're going to be using, to this end, KSMBD con. It's a structure in KSMBD that represents an SMB connection. So it lives in the kernel as long as the SMB connection is up. If we don't drop the connection, the KSMBD con object lives right there. And it has interesting fields for us. So it has the request buff field, which we talked about earlier, that points to the request currently being received. So that points to data that we control or will eventually control. It has other pointers to other valid objects in KSMBD, which could come in handy. And it's in Camelot 1K. So, okay, we have to trigger write leak on Camelot 1K to leak KSMBD con objects. So this time, we don't want to leak any random objects, so we'll have to spray connection objects. So basically what we do is that the slab isn't in some state. There are free items. We want to fill the slab and fill full slabs of our KSMBD con objects so that we can stop one of those connections that will free the item, that's the one in red, and then perform a refill with our right-click primitive, our right-click request that will fill that object and leak the next KSMBD connection in the slab. If we don't get anything, we can try that any number of times we want, but we need a way to know that we actually managed to leak a KSMBD con object. So how do we know that, and how do we know which of those we sprayed is the one leaked? So to do that, recall that in SMB2 negotiate, we mentioned earlier that the client sends a GUID. That GUID is stored in the KSMBD con object. So that means that, well, when we trigger write leak in the Camelot 1K slab after our spray, if the data we get back contains a GUID, well, we know it's a KSMBD con object, and we know precisely which one it is, because we just choose unique GUIDs for each connection. So that enables us to know that we leaked one object and precisely which one it is, and make use of its values. And those values contain notably a pointer to KSMBD module static data. So that allows us also to de-randomize the KSMBD load address. That will come in handy later. And so we've done our leaks. Now we can try to corrupt the heap to move further.
Okay, and that's my part because I'm the business owner of the write heap primitive. Okay, so we have leaked many information and many interesting information, thanks to Quentin. And now the question is that enough to corrupt heap objects and gain what we want to achieve, which is a stack pivot? Well, the answer is no, because a write heap is cool, but it's just a linear overflow, overflow in kmalloc 512. As we are bound to the KSMBD scope, we need to find KSMBD allocated objects that will fit and that we can overflow. And there are not much, because there are only 2 objects that may fit, and the only one that can fit is a KSMBD session. But at the beginning of a KSMBD session, we have an ID, which is just plain data. We can overflow easily. And there are 2 pointers that we'll need to cross and trip. And those ones, even if we have leaks, we have no way to set them to useful, interesting value, because the objects behind are complex objects made of other pointers, cross-referencing each other, which is not something we are ready to spray right now. So back to work, and we cannot corrupt heap objects that easily. But we will leverage the primitive that we have, plus one more primitive, in order to get the ability to forge objects into the kernel memory. As I said, KSMBD objects are complex, and our goal here is to be able to forge complex objects, meaning that in the objects we want to have list heads, which means that we can initialize memory with a content which points to itself, the address, got the value of the address itself. And we need to make cross-referencing objects into the kernel memory. So in this case, Spray wouldn't help us a lot, because we just don't know where the memory will arrive, so we cannot put the value that will correspond to the memory, to the address it will arrive. But looking back at the connection, which we leak, we see that there is a request buff, and request buff, as Quentin said, is where the data of the current request will arrive. So there is one thing that we could do with that. Looking back at the PDU handling, we see that at the beginning, there is a size, which is red, 4 bytes, which is red. Then the request buff gets allocated in the middle of the slide. You can see that there is a con request buff equals kv malloc. And in the TOPS read, the last TOPS read, this memory will be fooled with the bytes received on the TCP socket. So we control the size, and we control the content of the allocation. Now the question is, are we able to control the lifetime of this allocation? And digging into the function that is used to read the bytes from the TCP connection, we see that, yes, this is something that should be feasible, because first, there is a read-all mechanism, which means that if we set the size of the request to something big, then the function will wait for all those bytes to arrive before returning. And next, we can see even if there is a timeout which is set on the socket, there is something cool here, because if the receive errors with something that tells that there are no bytes currently available at that time, then the current thread will just nap and loop on, which means that it will resume to fill the buffer at the point where it's last filled, which means that there is a timeout, but due to the error in the code, the timeout will not work, and the function will just loop on and wait for all the bytes to arrive. So we can control the size of the allocation. We can completely control the content of the memory, because the function does not return, so KSMBD is unable to perform any kind of early parsing on what it receives. And we also control the lifetime of the allocation, because as long as we don't tear down the connection, the kernel will continue to read on this TCP connection and fill the memory with the byte that we send on the other side. So indeed, this is very cool, because this is a very powerful primitive. We are able to leak the address where the bytes that we will send will arrive, which means that we have a spray primitive first, and there is also more, because we know the memory, we know the address where the memory will arrive, which means that we can use addresses inside the data that we send, and that will be valid. So this is a third bug that we have submitted to ZDI, and this is the bug that allows us to forge kernel objects. So how do? We can, for example, take a huge size, like 1 megabyte, send this size as a net BIOS length, and then stop here, don't send the bytes. Using the leak primitive, the write leak, we can then leak the request buff, which is the address where the data will arrive when we send the data later, and then forge our object, send this blob data to the TCP socket, and then the content will arrive and the kernel will fill the request buff as long as we send the TCP bytes on the other end. And of course, if you don't want the kernel to free data, you just have to send less that you requested, and this allocation will be alive and filled with the data that you want to appear in your kernel at the given address that you know. So we have used this. We use the BTF information contained in the VM Linux kernel in order to get type information. We have a Jinja templating system that outputs a C structure. This C structure is the one that we will compile and link. We know the address where this structure will arrive, so we can use a linker script to make all the things run smooth. And once we have a blob, we send it to the TCP connection, and magically, this content will appear at the address that we know in the kernel. This way, we can forge objects like KSMBD user and KSMBD con, plus we know the content of this object, and of course, we know the addresses of these two objects that we send. This is an example of the C structure and the template. We can use the value that we have leaked before, and we can also use macros that make use of the ampersand, because the linker will know where the data will arrive, so all this will be correct. So now we can forge our objects in the remote kernel, and we can move forward with the corruptip primitive. So back here, last time we saw a red box. Now the box is green because we're able to overflow the object. We have a valid user pointer, and we have a valid connection pointer, which we may overflow a session object. Now what we have to fight against is that, recall that we are in kmalloc 512, and that there is a random free list, which means that in order to use our primitive, we need the object that we want to corrupt to be adjacent to the object that will be corrupted. And this is not very easy to get. So kmalloc 512 is a crowded slab, which means that this is a cache, and there are many slabs in it. There are many objects that are populated in this cache. So it also means that this cache is living quite fast, and the free list of this cache is always filled with many entries. So in order to have a chance to have a KSMBD session next to the reply buffer that we will overflow, we have one strategy that we have used, and is okay. We need to be able to fill as many slabs as possible with our target object, KSMBD session. This way, we will enhance our probability to refill a freed session in the slab with a target object, which will be surrounded by KSMBD session, right? So in order to do this, we need to be as quick as possible, and we need to take as many sessions as we can to fill full slabs. I mean, first draining the free object, the free list, and then be able to allocate in full slabs of KSMBD session. And this way, once we corrupt a single KSMBD session, we have chances to win and to overflow a session. So now the question is, how do we free one of the KSMBD session? We just have to cause an error on this session, and KSMBD will free the associated memory with the KSMBD session. So now we are making a hole in a slab, and we use write-tip to perform the refill with the target object that will overflow and overflow. It works, and we are very happy to see the kernel crashing as a first step, because we just replace the ID and the two pointer with bad values, and once we perform this trick of using a compound request to create that many sessions, it works, and we just overwrite the 24 first bytes of a KSMBD session, and the kernel crashes, so we know we are on the good way to perform. So we have successfully corrupted heap objects, and now the last step is how do we perform a stack pivot, because this is our ultimate goal. And we'll see this right now. Of course, as the KSMBD, the free list is randomized, which means that we are not 100% sure that we'll corrupt a good object. So there is one test that we can do. We override the session with a marker here, food, and we're gonna try to perform, when we perform any action on this specific session, we can know if the overflow has succeeded or not by observing the response of the SMB reply. If the reply failed with the cause user session deleted, it means that the overflow did not work, and we can retry later. And if we don't receive this kind of error, it means that we have successfully overflowed a KSMBD session and that it worked. So now the question is, when the overflow works, what can we do? We are looking for some indirect function call that we control, and in fact there is a path between SMBD session setup, which will perform the NTLM handshake, and one indirect call here, which is a code page card2uni function, which will be called. This path here is okay because now we control the session. We have overwritten the session with a fake con pointer. Then we can control the local NLS, which will be used to dereference the memory and to perform the indirect call later. So now the question is, which gadget could we use in order to stack pivot, now that we control the function that will be called? And of course, there is no absolute answer to this question, and it highly depends on the environment. Here we have seen that when the call is performed, there is a stack word 3 steps below us. That is cool because it contains a pointer to the input request that we have submitted, which means that we control the input request, we control the content, and we can find a gadget that will perform a stack pivot to this controlled area, and then we are good to go. So we found a gadget, which is basically a move RSP, and it moves the pointer to RSP. So, high-level view. This is the originating stack at the moment of where the gadget is called, and what we do is that we perform a first stack pivot onto our input buffer, here on the top, and we make a second use of the very same gadget, because this time we will control the value that will be popped from the stack, and that will become the second stack after. And this way we can perform a second stack pivot, but this way leading to our fake stack, and we fully control the stack, which will we pivot to. So we have successfully performed the last step of our attack, the stack pivot, and we just have to fill a stack like this. For example, we can call user mode helper, which will spawn a user space process on our machine, and it will make a reversal, connect back to our machine, and I mean, we are finished with the exploit, right? I believe it's demo time, and next we'll see questions. So just give me a few moments for the demo to work. Okay, so here's my jammy machine, which is the victim machine. Oh, yeah, you see. And this is my machine where the exploit will run. So this is the netcat listener. And here we first perform the step of leaking the kernel base. So it works fast and it's nice. We have seen here the 10 matches that it has extracted from the dump of the kernel heap memory. And we have 10 points that matches, so we know that the kernel base is very likely to be this one, and very likely means like it is this one. And now we use the value that we have, and we have to set a parameter that tells the script how many attempts it will try to leak KSMBD connection. So now we have all the different steps that I've performed, and you see the result on the screen. And if we check on the netcat connection, we can see here that there is a root shell. And that, of course, it works, and the date works okay too. It's not a fake machine. And if we look at the release, this is the release. Quentin? Yep.
Okay, so it worked. We had a backup ASCII-NEMA, but okay, so it's not fully reliable. We may the sprays may not work. We may overflow into something that's not a KSMBD session object that's being used, and that will actually crash the kernel, but it's pretty reliable, and well, it has worked well so far. Okay, so that was our first flurry of findings in KSMBD. We had another session, and we now have our own branch in the KSMBD upstream repo because it doesn't work well with concurrency, and this actually hindered us during exploitation because we can't hammer it too hard with requests, otherwise it just crashes and nothing works anymore. So those bugs were really annoying while developing the exploit. So we want to thank Arnaud and Florent. They were part of this. Our team, Thallium, for allowing us to work on this and publish the results. The DI for the disclosure, they were really helpful with all that. We know that kernel disclosures are usually, well, they can be quite tricky. And OffensiveCon for having us today. Thank you all. Take questions now.
Yes.
How sensitive is it to the exact version of the person?
So how sensitive is it to the exact version of the kernel? Actually, there are KSMBD changes a bit during among the versions. It's quite. I mean, it's still a work in progress. So there are quite a few changes among the versions. We actually admit ourselves to leaking only one slot after the one the request is in when we trigger write leak, because in further kernel versions the check is a bit different, and we can't leak any length of bytes we want. So the difference would be the addresses in the slabs. We need to profile it for every kernel version to see where the addresses are, what objects we can find in the slab, and what the addresses would be. And so we have to rebuild offsets for basically every version. But other than that, the primitives, if they are not, well, up until the point where they are fixed, they are quite stable.
Okay.